Hello and welcome back. And today we have some more exercises, and in particular, they're going to be on determinants. So, as usual, let's start and solve the given exercises. And while solving these exercises, I'm also going to give you some few theoretical recollections, just a little, just a few of them, and then after we've solved the exercises, as usual, I'll give you the tutorial on how to write the detailed solutions of those exercises. So let's get to the first one. So we have a matrix, and it depends on a parameter. So you see here this parameter. And the first question asks for which values of the parameter this is invertible. Okay, now the goal is to use determinants here. So let's recall just a few practical things about determinants. So if you have a, I don't know, 1 by 1 matrix, for example, this, then the determinant is just the number itself. Okay? If you have a 2 times 2 matrix, like this, the determinant is given by this formula. And more in general, if you have, say, a matrix which is like this one, let's take just this one, what you should know, 1 minus 1, 1, 2, 1, 0. Okay. What you should use here is the Laplace formula. This is very useful. So the idea is that you can compute the determinant this way. So first you put t times, it's t times minus 1, 1 plus 1, and I mean this gives the row index and this gives the column index. You follow this row here times the determinant of what's left, and then if you go on, theoretically is like plus 0. So you follow this row, and then the idea is that at each time you cancel. I mean, for example, here we started with t, then you cancel this row and this column, and you take the determinant of what's left. Okay, so if you follow again this row, then you have 0 times minus 1 to row plus column index times the determinant of what's left by erasing this and this, which is like in theory 1, 1, 2, 0. In practice, it's not really necessary. And then you go on following this row and this 0. Then you have the row and column indexes. So it's 1 row index, 3 column index, times the determinant of what? Of the matrix you obtain by erasing this and this. So it's 1 minus 1, 2, 1. I mean, of course, since this is 0, then you don't have anything here, and so what's left? It's actually this thing, and this is true, so it's actually kind of easy. So it's t times the determinant of minus 1, 0, 1, 1. And now this is a 2 times 2 matrix, so you know how to compute the determinant. So it's like t times minus 1. So it's minus t. Okay, and then from the theory we know a square matrix. And don't forget, determinants exist only for square matrices. Matrix A is invertible if and only if the determinant of A is different from 0. So in this case, let's say a square matrix, not this A, let's call this B. So in our case, we conclude that determinant of A, so A invertible, if and only if determinant is different from 0, if and only if minus t is different from 0, so if and only if t is different from 0. So this is the condition. Okay, very good. And okay, that's for the first point. So let's see here. Okay, the second one, compute the determinant of A to the 2020th power. So this, well, you have a formula in general. You have this formula, namely that the product of the determinant of a product is actually the product of the determinants. So in particular, the determinant of a power is actually the power of the determinant. It's very nicely behaved. And so, I mean, it's easy in this case because here you have minus t to the 2020. So, I mean, this is even. So you can conclude, if you want, that this is t to the 2020th power. Okay, I mean, nothing strange here. So, okay, so the third one, don't be fooled by this. It asks, compute the dimension of the kernel in the image if t is equal to 1. So, of course, you could, in principle, take t equal to 1 and solve some linear systems and so on. But here, I'm asking just dimensions. So, recall, just be smart here. For t equal to 1, since the determinant is minus t, the determinant of A is equal to, what is it, minus 1. So A is invertible. This we know from the theory. We conclude that, I mean, you can conclude that the system Ax equal to 0 has only one solution. This is x equal to 0, namely the kernel of A is trivial. Then you recall that 3 is equal to the dimension of A plus, dimension of the kernel plus the dimension of the image. So we conclude, so from here you conclude that the dimension of the kernel of A is 0. Just don't forget, the kernel is trivial, the dimension is 0, so it means that a basis has to have 0 elements, so basis is the empty set. So don't make the mistake of saying that the 0 vector, this is the 0 vector, that's the caveat, so be careful, is not a basis of anything. The 0 vector is never a basis. A basis of this space is the empty set. Let me write it like empty set. It has to have 0 elements. I mean, just a caveat here. So the dimension is 0, so you conclude that this is 0, so this has to be 3. I mean, you're done. You don't have to do any computations here. And even the last one, I mean, you have to be just careful. I mean, when you have an exercise, always always look what you are asked for. Don't just start like doing computations mechanically and possibly lose a lot of time. So here I'm taking this B and I'm asking, consider this linear system and tell for which t this system has no solutions, exactly one solution, or infinite solutions. I mean, this is important. I don't ask you to find the solutions. I'm just asking you to say, is this unique? Does it exist? Are there infinite solutions? So, well, we just have to look. So take B if you want. This is the, what is it, the fourth. So take B, this vector, and so recall the theory tells that if A is invertible, this is general. So the system Ax equal to B has exactly one solution. One solution, and it's given by taking the inverse and then computing this product. I mean, it's not important what this actually is. The important thing is that you have a unique solution, and this you know from the theory. So in our case, if t is different from 0, then has exactly one solution. So it remains to look t equal to 0. We have to look. I mean, this you can't avoid. So because it can happen that you don't have solutions, or perhaps you have an infinite number of solutions. So it depends, but you have to look at it. But I mean, here it's kind of easy, because if you take if you take t equal to 0, then you have this system 0, 0, 0, 1, 1 minus 1, 1, and 2, 1, 0, I think. And if you want this equal to, sorry, 1, 1, 1, fine. Yes, is it correct? So, I mean, but if you look at this, you immediately find this. I mean, you can even stop here. From here, you find out that no solutions. So yeah, you're done. We made it, and that was it. I mean, you didn't have to compute the solutions. Just like use the theory and be smart. I mean, sometimes you're not asked to do a lot of efforts and compute stuff. You just have to like look carefully at what you're asked for, and just try and use what you know, and find the smartest way to achieve the solution of the exercise. So okay, so that was it for the first one. So let's go to the second one. Okay, this is a little more theoretical, but it's nice because it's an opportunity to say an important thing. So a couple of important things. So you take n to be an odd number and A to be n times n matrix, such that it's equal, its transpose it's minus A. So this is sometimes called skew symmetric. If you want, skew symmetric. Okay. Is it? I think so. Let me check. Yes. And you can see there are things of the form like you have to have a 0 and then on the diagonal, and then you have things like this. I don't know. This is an example if you want, but it's not really important here. And you have to prove that A is not invertible. Well, we know that invertibility can be checked with the determinant. So we look at the determinant of A. And so now we have to recall a few theoretical facts. One is important, namely that the determinant of the transpose is equal to the determinant of the original one. So this is important. Don't forget this. But now the transpose is equal to minus A, so this is determinant of minus A. Okay. Now let's be careful here. So let me say what the naive student would do. It would write something like, let me write here orange. It would write something like, in general. And I mean, it's important to say that this is in general false. False. But we'll see that actually in this case, even the lazy and naive student would have got it right. So well, but that would have been luck, not expertise. So let's be careful here. What happens in general if you want to compute the determinant of lambda A for some lambda? Well, let's be careful here. What you can do is like write this product here as follows. So this is the determinant of lambda times the identity times A. I mean, this is perfectly good, right? So the identity matrix, this is A. You can also rearrange things like here, like this. So this is lambda times the identity times A, and then you use the known formula, which says this. Okay, so you have the determinant of A here, and then we have the determinant of lambda times the identity. So this is a matrix like this. And you know that for diagonal matrices, the determinant is just a product of elements of the diagonal if the matrix is diagonal. Not in general, of course. So in this case, it's what? This is n, so it's lambda to the nth power. So we conclude that determinant of lambda A is actually equal to lambda to the nth power times the determinant of A. And in our case, the determinant of minus A is the same, if you want, as the determinant of minus 1 times A. So it's actually minus 1 to the nth power times the determinant of A. And if n is odd, then actually this is equal to minus the determinant of A. So in that case, as I said, we were lucky. But not in general. Well, just another thing here. Let me just say that the determinant can be computed as the product of elements of the diagonal if the matrix is diagonal, but also if it's like upper triangular or lower triangle, if you have something like this, or if you have something like this. So in that case, the determinant is very easy to compute. You just have to compute to take the product of the elements of the diagonal. It's very easy. Okay. But let's go back to our exercise. So we've said that the determinant of A transpose is equal to the determinant of A, but this is equal to the determinant of minus A, because like A transpose is equal to minus A. And this is minus 1 to the nth power, in general, times the determinant of A. But since it's odd, this is minus the determinant of A. And from this, we conclude that you look at this and this, these are equal, so you conclude that 2 times the determinant of A is equal to 0, but then it's necessarily the determinant of A has to be equal to 0, so A is not invertible. Okay, and that was it. That was it for the second exercise, and we'll write it nicely later on. So the third one, okay. Now, this is just a computation, but it's a nice occasion to say something more. So, I'm giving you these two matrices, and I'm asking you to compute their determinant. And the hint here is use matrix row operations. So, the thing is that you can use the matrix row operations to compute the determinants, because you can. The point is that you can modify the determinants of those matrices using these matrix row operations, but in a controlled way. And in this case, it's actually the nicest thing happens actually, because because there is actually one row operation which doesn't change the determinant, and namely the row operation of replacing, let's say, row R with R plus A times row. This is, yeah, another row. And A, this is a real number. Does not change the determinant. Okay. So let's try to apply this rule here. So let's look at this. We want to compute the determinant of this, but as I said, it doesn't matter if we do this row operation. We don't change the determinant. So for example, here we can take the second minus A times the first as replacement for the second. So here you get this, and then you get 0. And yeah, B minus A, C minus A, okay? And here we can take the third minus what? A squared times the first. So it's 0, B squared minus A squared, and C squared minus A squared. Okay, very good. Let's see if we can do something more. So let's decompose, let's go on a little bit. This is again 1, 1, 1. Oh, sorry, handwriting, bad handwriting. So 1, 1, 1, and here's 0. B minus A, C minus A, B. Let's decompose this. B plus A, and yeah, let's also decompose this if we want. Yeah. So now let's see. It seems sensible to take this and this to be equal, and then replace the third by this minus B plus A, the second. So what happens? 1, 1, 1, 0, B minus A, C minus A. Fine. Okay, so then here it's 0. Here it's again 0, and here it's something like C minus A, C plus A, minus B plus A times C minus A. Very good. Okay, so let's write it nicely. So we get, I mean, the point is that after these operations, the determinant, the original determinant, didn't change. So we are left to compute the determinant of this matrix. And this is, yeah, let me just simplify things a little bit. So we can do this, C times A, and then factor like this, C plus A minus B minus A. So this is, if you want, C minus B. Yeah. And so we are almost there, actually. Yes, so I've told you, but you can check it with the Laplace formula if you want, along this column, which you can also do, that the determinant of an upper triangular matrix, so something like this, is actually given by the product of the terms in the diagonal. So after summing up, so you have this original matrix. We've said that these row operations don't change the determinant. So the original determinant is actually the determinant of this, and this product here, B minus A, C minus A, C minus B, which is, I think, quite a nice formula to have. And yeah, let me just check if I got it right, but I think so. Yep, it's okay. And yes, and as for the second one, it's actually a, well, it's actually a what is it? It's not really a different question, but determinant of B, well, if you look here, it's actually, I mean, if you change variable, call a squared to be, I don't know, a squared to be a prime, b squared to be b prime, c squared to be c prime, and then you're back, in the, if you see, then you get b is equal precisely to 1 a prime, a prime squared. So, I mean, we already know this. So, in the end, you get the determinant of B is equal to, yeah, you can just replace. It's the B prime, C prime. But yeah, after you just replace. So it's nothing. I mean, it was not really. It was like when you observe this, you don't have to do anything else. But yeah, it's when you know this, you also know this. It's like a trick, and this is always for students, for everyone, just not do things like mindlessly. So try and be conscious of what you're doing and what can ease your work and make you save time and energy. I think this is one of the most important things you can keep in mind while doing mathematics. So doing mathematics is really trying to use your energies in a smart way, finding like avoiding stupid hard computations, and instead finding smart ways of doing this, and with that saving a lot of time and energy, and be able to do more powerful things. Okay, so that was it. It was not very difficult. So what about the fourth one? I mean, this is, and this last exercise is actually very very straightforward, because you should just know a piece of theory here. So recall let's say that if you have a matrix A, B, C, D, let's say just 2 times 2, then if you take the determinant and you take the absolute value is equal to the area of the parallelogram spanned by the column vectors. So, well, it's nothing strange, right? So here, to conclude, to find the area of the parallelograms whose sides are given by these vectors, you just have to compute the determinant of 1, 1, 1 minus 1, which is, I mean, we know the formula here, and taking the absolute value here, so it's, what is it? So minus 1, which is the absolute value of minus 2, which is true, and here again the determinant of 2, 1, 1, 2, taking the absolute value, so it's like 4 minus 1, which is the absolute value of 3, which is again 3, and you're done. Yeah, so there's nothing strange to say here. Well, it was pretty doable. Well, fortunately, this time we didn't have a lot of very difficult exercises. So, okay, let's write the solutions now, finally. Okay, as I said, new thing. Okay, so now the solution writing tutorial as usual. So the first exercise. Well, mind your handwriting. I mean, it's not really that important, but if it's nice, it's an advantage, which probably not in my case, but yeah, sorry. Okay, so as for the first exercise, okay, and we have 4 points. So 1, let's just be detailed. So we compute determinant of A using Laplace so determinant of A is going to be T times the determinant of minus 1, 1, 1, 0, okay. And this is it. You don't have to write the other parts, the 0 parts. I mean, it's okay. This is part of the theory, and if you apply it correctly, it's okay. So it's like now it's T times minus 1 minus T. We know that A is invertible if and only if. Well, if you don't like to write if and only if, you can also write this word, an if with 2 F's, which stands actually for if and only if. But it's a nice thing to say to remember if you want. Okay, if and only if the determinant of A is different from 0, so if and only if T is different from 0. So I mean, here I just didn't write minus T different from 0, which is actually the same as T is different from 0. I mean, this kind of things we can omit. I mean, minus T different from 0 is the same as T different from 0. That we can omit safely. Okay, this is it. This is for the first part. So the second. So we have that. You can just state this is equal to determinant. Mind the parentheses, of course, which is minus t, which is equal then to t to the. That's okay. You don't have to write more than this. I mean, this is part of the theory. This formula here, it's perfectly known, so it's okay. This is it. Okay, 3 here. Okay, since A is invertible, we know, and this we also know from the theory, we know, sorry, if t is equal to 1, then determinant of A is equal to minus 1, which is different from 0. So A is invertible. We conclude that the kernel of A, this is also part of the theory. If you have an invertible square matrix, then you know that the kernel is trivial. And you also know that the rank is maximum. And so hence dimension of the kernel from the identity three equal to we conclude that dimension of the image is equal to 3. Okay, that's okay. That's perfectly okay. So okay, and for the fourth one, okay, we call, if you want, okay, this is interesting. If you want to be really neat, you can recall from some other point. We recall from 1 that I mean, this is kind of even more than what's needed. So I mean, don't worry. This is just like, I want to be super detailed, but it's nice to put these cross references sometimes. It's a nice thing to do. We call from 1 that A is invertible if and only if t is different from 0. So if t is different from 0, the linear system Ax equal to b has exactly one solution given by, I mean, it's not, I mean, this is not really necessary, but if you want just to say this, it's okay. It's not really important to say what the solution is. You can also omit this part. You can omit. But yeah, I like to. I just wanted to add this. Just yeah, for the pleasure. I just like to have it written down. So, but it's not necessary. Okay. Exactly one solution. If t is equal to 0, we we have the linear system 0, 0, 0, 1 minus 1, 1, 2, 1, 0, really? X, Y, 1, 1, 1, which yields I'm writing everything, but you can also conclude. You could also conclude here if you wanted it. X. From which we deduce that the system has no solutions. And this is it. Let me see if I've written correctly. 1 minus 1, 1, 2, 1, 0. Yes. This is it. This is it. I mean, but, yeah, of course, you can conclude immediately at this point. You could conclude, or by looking at this order matrix, you can conclude. I mean, it's when you have this, it's like, of course, you immediately conclude. You don't have to make any more explanation. So that's for the first one. It's okay. Let's go to the second one. Okay, let's add page here. Okay. Now here it's going to be very short. So exercise true. Okay. We have by hypothesis, this is our hypothesis, we have, no, let's first say that we recall that the determinant of A is equal to the determinant of the transpose of A. Then by hypothesis we have the determinant of A is equal to the determinant of A transpose is equal to the determinant of minus A and moreover the determinant of minus A is equal to minus 1 to the n, the determinant of A, which is equal to minus the determinant of A since n is odd. We conclude that, so here write determinant of A, determinant, well, is equal to minus the determinant of A, from which we deduce 2 times the determinant of A, hence determinant of A equal to 0. So A is not invertible. As claimed. Okay, this is it. This is it. this is it. This is it. Well, probably the handwriting could be better, but yeah, the exercise is done. Okay, fine. Okay, so this one. So exercise 3. Okay, we recall that replacing of A with R plus, I don't know, X times R prime another does not change the determinant. So we can modify does not change, not say net A, does not change the determinant. You can modify A as follows. So one comment here: it's nice when you write a detailed solution that, okay, you know that pieces of theory you can use, of course, but it's nice and advised and a very good thing to do that you recall specifically what pieces of theory you're going to use. So when you, as I said, for example, here I've written just a few words by saying that we recall that we have this thing that if we have a matrix and we replace one of these of its rows with this, I mean this itself plus a multiple of another row, I mean then the determinant doesn't change. So it's good that we recall this, and it's always advised that in general when you write a solution, then you just recall the necessary theory and you just rewrite it. I mean, synthetically, you don't have to rewrite the entire book, but just what you need, so that who reads can be convinced. I mean, they look at your solution and they say, okay, so he's using this and this and this, and he put the references, and it's nice, yeah. So it's good that we do something like this. Okay, and then we go on with the solution. So so here, if you want, you can okay. Okay, so let's write it. This is a little bit tedious, but not so much, fortunately. Okay, so now here you replace the third, okay, third by the third minus b plus a, the second. Now I need more space here. 1, 1, 1, 0, 0. B minus a, 0, C minus A. Okay, so we can compute even here C minus A, C plus A minus B minus A, C minus B. Okay, so which is, if you want, then so determinant of A is equal to the determinant of this guy here, which is equal to the B minus A, C minus A, C minus B. Okay, you don't have to recall, I mean, it's up to you. If you want, you can also recall that the determinant of upper triangular matrices is given by the product of the terms of the diagonal, but I mean, I decided not to take it for granted at some point. I mean, I've said before that it's nice to recall pieces of theory, but of course, remember what we always say about writing solutions. It's your choice. I mean, if you think that a piece of theory is really relevant and it's really crucial that the reader sees a reminder, then yeah, go on and make this reminder. But if you think that perhaps you don't really need it, and perhaps who reads has seen enough to, for example, remember that determinants of matrices like this are given just by this, it's okay. I mean, in general, if you want a general criterion, then I'd say if it comes down to just computing stuff, then it's safer to avoid reminders. But if it's more theoretical stuff or more crucial stuff, like tricky theoretical things, then it's better to recall and be detailed. But I mean, in general, if you want, if it just boils down to computing things, then it's safer to avoid saying everything. So to avoid really be excruciatingly detailed. So, but it's up to you. I mean, your goal has always to be a nice solution, and it's up to you. It's also your style at some point, and it's not that there's a better style than and a worse style. I mean, there are mathematical books which are written like in a really concise style, but still they're much appreciated, even if they don't say, perhaps they omit a lot of details, but they still give the interesting points and the interesting ideas, whereas other books are very detailed and they give you everything, and it's also okay. I mean, it's up to you. I mean, as beginners, I just suggest you, in doubt, be more detailed. But if you want to take some risks, and if you think it's okay taking these risks, then go on. And just keep in mind that your goal has to be a good experience for the reader. I'm going to repeat it again and again, but it's important. So here I decided that I could avoid saying that the determinant is computed by looking at the terms in the diagonal, or like doing the explicit Laplace formula. Also because, I mean, in the first exercise, I've already mentioned that here it was was more important because the first point of this exercise was just really compute this. So it was important to justify and detail this instead of just like doing this and not writing anything to justify this. But I mean, now if you want, the reader has already seen this kind of computation, and you can assume, if you want, that they can do this by themselves. So you don't have to redo it. So that's why I decided to avoid like writing an explicit computation of this, or to give more details. But as I said, it's kind of up to you. Take your risks. Just think about it. Be clever. Be smart, and just think. If I were to read this solution sheet, would it be okay at this point to omit these details? If you think so, then okay. You're taking a risk, but yeah, okay. If you don't think so, or if you just want to be safe, then just write every detail. If you just want to be safe, just write down every detail. This always works, and it's normally kind of appreciated too, because yeah, you can skip when you have every detail written down. The reader can skip them if they want to. And it's okay. But if you take risks and you omit some details, then the reader can be like just there and think, and what now? What did they do? Why is this happening? Is it good? Is it correct? Am I lost? And yes, you probably want to avoid this. So as I said, take your risks. Normally, in this case, this kind of computation we already done before in the first exercise, so it's kind of safe to omit it, and in any case it's just a computation. So we are in the safe. We are still in a safe space. But as I said, it's up to you. Let's go on. Okay. Okay. Here, the determinant of B is computed by let's write this. For matrix B, we make so that this is kind of easy, so you can use the above. And conclude. Okay. Okay. So, okay. Yeah, it's okay. Neat. Fine. The last one. Yeah. This is kind of easy, but yeah. Okay. Give names. So 1, 1, 1 minus 1. 1 true, 1 1 true. The expand SE, you have names here. S1, S true, SE, so E equal 1 or true is given by namely and yeah, this is kind of like sorry, this is A1. Sorry. 4 minus 1, 3. This is it. Done. So this time it was like a little quicker than before, fortunately. Okay. And good. Yeah. Exercises on determinants are probably the easiest ones you can encounter in linear algebra, but okay, we made it. And yes, so there's nothing more to add, I think. Let me just check. But it's correct, right? True 3. Yeah. Okay. So yeah, this is it. And yeah, so see you next time.